This is the lesson for pre-calculus for section 7.4 day 1 on April 27th, 2018. Quick reminder for everybody, and I know I've reminded you every day for 3 days in a row now, but juniors, the MCA's on Monday. Remember to bring your fully charged Chromebook, earbuds and headphones, graphing calculator, pencils, your noggin, and paper book to read. Again, on Monday, you probably won't need to bring that paper book. You should be working on your test the whole time, but have it for Tuesday and Wednesday. So now, we're going to talk about section 7.4, which is a really fun section on partial fractions. So stop right now and take out those state concepts and pre-rate yourself on those 7.4 concepts for partial fractions. And that is going to be 7.4, I can use partial fractions, I can write decomposition factors, I can decompose a fraction with distinct linear factors, I can decompose a fraction with a repeated linear factor, I can decompose a fraction with an irreducible quadratic factor, I can decompose a fraction with a repeated irreducible quadratic factor, and I can apply knowledge of decomposition of partial fractions to graphs. So, like I said, please pull out the yellow packet, pause the video if you need to, and pre-rate yourself. Now on to the lesson. 7.4 is about partial fractions, and this is really gearing us up for calculus because there are times when we have to decompose a function so that we are able to do all of the math that we need to do in calculus. So our objectives, we will be able to write decomposition factors, decompose a fraction with distinct linear factors, decompose a fraction with a repeated linear factor, decompose a fraction with an irreducible quadratic factor, decompose a fraction with a repeated irreducible quadratic factor, and apply our knowledge of decomposition of partial fractions when graphing. So using that to figure out to our advantage what would some pieces of our graph look like. So with partial fractions, partial fraction decomposition is what we're looking at. So a polynomial with real coefficients might be factored into a product of factors with real coefficients, where each factor is either linear or an irreducible quadratic factor. So some keys here is the reminder that x to the first, if 1 is the highest degree of your polynomial, that guarantees that it's going to be linear. Now, when they say irreducible quadratic factor, what they mean is you have a quadratic, which is a degree 2 polynomial, which is not factorable. I've got x squared plus 3x plus 1 up there. We can't find two integers that multiply to 1 and add to 3. It isn't going to happen. So that would be called an irreducible quadratic factor. And things like that happen as you're trying to factor. For instance, we see here x cubed minus 64. And it has been a while since we have had to do any factoring of this nature. So I want to remind everybody that 64 is a perfect cube. So this would be the difference of two cubes. And what we would pull out of our memory banks is that when we factor a difference of two cubes, we do get a linear factor of a minus b. But along with that, we have a squared plus ab plus b squared. And now a and b are what did you cube to get x cubed, which in this case would have been an x, and what did you cube to get 64, which in this case is a 4. So if we break that into its factors, it will be x minus 4 times x squared plus 4x, and then if you square 4, you'll get 16. So we have just broken this up into a linear factor, and that's this x minus 4 that we see right here. That is definitely an x to the first, so that is linear. And then I'm wondering, okay, is that factorable over there? X squared plus 4x plus 16. So we quick run through our list of numbers that multiply to 16 and add to 4. And we find out there aren't going to be any. We've got 1 and 16, 2 and 8, 4 and 4. But just to make sure, remember you can always use the discriminant, and that's our little b squared minus 4ac. Now, to be factorable, that has to come out to be a perfect square. So we use our ax squared plus bx plus c, standard form for a quadratic, and this would be 4 squared minus 4 times 1 times 16. That's going to be 16 minus 64. That's a negative 48, and a negative is definitely not a perfect square. So the fact that it's a 48 is really a non-issue because we are getting a negative there. So that means that our ax squared plus bx plus c that we have here, x squared plus 4x plus 16, is an irreducible quadratic. It's quadratic, it's a degree 2 polynomial, but it cannot be factored any further. Irreducible. So when they talk about those irreducible factors in the future, that's what they mean. We can't keep going. So in this section, we show that a rational function can be expressed as a sum of rational functions where each denominator is a power of a linear factor or a power of an irreducible quadratic factor. So we break it up and we try to figure out what we have. So this is going to be quite the thing that we do here when we're going through this. So we needed that little sound effect. This is a process. Now I would say it's not a difficult process, but it's a process. So we want to make sure that we can do all of this as we go through it and that we can remember all of the steps. Well, the first thing that we need to do is say, what on earth is all of this about? What are we going to do? Well, each fraction in the sum is a partial fraction, and the sum is a partial fraction decomposition of the original rational function. What on earth are they talking about? Well, they're saying we might have this big, huge answer for a fraction answer for a problem, and we may need to work backwards and break it up into smaller pieces that we can do the math on. Let me give you for instance. If we rewrite 3 over x minus 4 plus 2 over x plus 3 as a single rational expression, we would start by realizing we definitely have some fractions here. I mean, that is obvious. And if you are going to add two fractions together, you have to have a common denominator, and the hope would be that you use the least common denominator. Well, in this case, that's going to be both of these linear factors that we see in the denominator. So this one would need an x plus 3 on the top and the bottom, and this one is going to need an x minus 4 on the top and the bottom. And once we do that, we will have 3x plus 9 over x plus 3, the quantity x plus 3 times the quantity x minus 4, and then we'll have plus 2x minus 8 over the quantity x plus 3 times the quantity x minus 4. And we realize we do have a common denominator, so we go ahead and actually do the addition. 3x plus 2x is 5x. 9 plus a negative 8 would be 1. And we have that over our common denominator of x plus 3 times x minus 4. And the last thing we would look for is, can we do any canceling here? And the only way we could do any canceling is if 5x plus 1 were factorable, and it's not. So that's our answer. Now, what we want to do is take this answer and be able to break it back up into these two components. That's what we want to do. Because again, sometimes the math that we need to do in calculus cannot be done on 5x plus 1 over the quantity x plus 3 times the quantity x minus 4. But if we break it back up into these two fractions, it's possible to do the math. So this section will give us techniques to perform this operation backwards, to break it up, to make those into partial fractions. So it says the partial fraction decomposition of f of x over d of x. Notice that f of x is going to be the numerator and d of x is going to be the denominator. And we think about that as we're reading through this. The degree of f, so the numerator, is greater than the degree of d, the denominator. So if the top has a bigger power than the power on the bottom, use the division algorithm to divide. Yeah, you should be able to divide. You have a bigger power on the top than you do on the bottom. Now when you divide, you're going to get a quotient, so an answer, but quite possibly you will also get a remainder. And we know that we always write that remainder over the divisor. So that would be a way to see, okay, now can I do the math that I need to do? In 2, it says factor that denominator into the product of factors, whether or not you have linear factors, which are the easiest to work with, or quadratic factors, but those have to be irreducible. We really, really want linear factors if we can get them at all. So we have to make sure that our quadratic cannot be factored. For each factor that you see, each linear factor, mx plus n to the u power, the partial fraction decomposition of r of x over d of x, and that's going to be this remainder piece that we see back here, must include the sum. Now notice, we have a over mx plus n. And I know it says a sub 1 and the next one says a sub 2, but that gets really messy. So what we're going to do is we're going to put a over a linear factor, and then we'll put a b over that linear factor to its power. And how do we know when to quit? When we have the highest power of our linear factor from the original, which was step number 2. And that'll make more sense as we go through some of these examples. But we have to have every single power there. So let's say that one of our factors is x plus 2 squared. This is saying it could be just an x plus 2, but our denominator could also have an x plus 2 squared as part of it, and we have to account for that. And then for number 4, it says, for each factor that we have that's quadratic and irreducible, the partial fraction decomposition of that remainder must include the sum. And here's the really big deal. We have to remember that these must be irreducible. Irreducible quadratics. If we can factor them, we're going to continue to factor them, and we're going to get some linear factors and work with it that way. So this would be our sum. Now notice, when you have irreducible quadratics, it's not just a and b anymore. You have to use one less degree than what you have in your denominator. So if our denominator has quadratics in it, then we have to use linear terms in our numerator. So the partial fraction decomposition of the original rational function is the sum, q of x, and the fractions in parts 3 and 4. We are taking a fraction and we are breaking it apart. And as it says in the black here, partial fractions are extremely useful for integration in calculus. So we'd better learn this, and we're going to have to learn it in steps. So here we go. We're going to start pretty basic, and then we'll go from there. Example 1 says we want to write the terms for the partial fraction decomposition of the rational function 5x minus 1 over x cubed times the quantity x plus 3 times the quantity x squared plus 1. So remember, we are trying to break these apart. So it's quite possible that this x cubed was just an x, and then maybe it was an x squared. So we have to reckon for that. So like it says, we don't want to solve this one. All we want to do is write it. So that means there could have been some numerical value a over x. That could have been one of the fractions. Plus, could have been some b over x squared, because together those would have a least common denominator of x cubed. But we definitely, or of x squared, we definitely need the x cubed piece to know, okay, now building this fraction up, we would see we have to have an x cubed. So notice we take every power possible for that x cubed. X to the first, x to the second, x to the third. Now, the next factor we see is an x plus 3, and that's linear. So we'll make that d over x plus 3, but that's its highest power. So we don't have to do any more with that one. That's all that's going to show up. And then x squared plus 1, well, we'd have to think about that for a minute. We'd have to think, is x squared plus 1 factorable? Can you find two numbers that multiply to 1 and add to 0? And you can't. That's not going to happen. So this is definitely an irreducible quadratic. And we have to keep in mind that what we put in our numerator is 1 degree less than what we see in our denominator. So we need a linear piece up here. So EX plus F would work great. So this is how we start, is just by thinking about, okay, what are all of the pieces going to look like? How is this going to work? So you're going to have some problems where all you're doing is you're saying, okay, what could this possibly break apart into? And that is the decomposition. So now what we need to do is take it a step further and actually start trying to find some answers to this. So examples 2 and 3 will show us how those constants, and again, the book uses a sub 1, a sub 2, a sub 3. We're not going to do that. It's much easier to keep track of everything with A, B, C, and D. And it says it shows us how to use those constants in part 3 of the partial fraction decomposition procedure and how we can find those. So decomposing a fraction with distinct linear factors. So that means we're going to start off with baby steps, and this one is not meant to be incredibly hard. It says find the partial fraction decomposition of 5x minus 1 over x squared minus 2x minus 15. The first thing we have to do is see whether or not we can factor that denominator. So let's leave the numerator alone, but take a look at that denominator and realize that there's no greatest common monomial factor. There is nothing special about this. It is not a perfect square trinomial because we have a negative 15 in the back. That is not a perfect square. But we need two numbers that multiply to negative 15 and add to negative 2, and that would be negative 5 and positive 3, multiplying to negative 15 and adding to negative 2. So what that tells me is there was some a value over x minus 5 that could have been added to some b value over x plus 3 that when you actually did the addition came out to 5x minus 1. So what I want to find is that a and b. So here's what we do. We just pretend for a little while that it is just a and b. And we think about what we would have to do to these fractions to get them together back to the answer, which was 5x minus 1 over x squared minus 2x minus 15. And we realize that would mean that this first one would need an x plus 3 on the top and the bottom, and the second one would need an x minus 5 on the top and the bottom. And we see what happens when we do that. So if we distribute the a, we're going to get ax plus 3a over the quantity x plus 3 times the quantity x minus 5 plus, distribute the b, bx minus 5b over the quantity x plus 3 times the quantity x minus 5. And now we could actually put those together. They have the same denominator. The quantity x plus 3 times the quantity x minus 5. So if we were going to actually do the addition, we would notice, hey, two of these are x terms. So we'll have ax plus bx plus 3a minus 5b. And that sets us up for what we need to see. So we have this, ax plus bx plus 3a minus 5b. And remember, keep in mind, the goal here is to get this back to 5x minus 1 over x squared minus 2x minus 15. Now here's what I know. I know that these two have x's in them, and I see this is x. So ax plus bx has to equal 5x. And then I see that these apparently are just constants. There's no x there. So 3a minus 5b has to equal -1. And I think, well, you know what? I don't need those x's. It's the numbers for A, B, C, and all of that good stuff that I really need. So this will be A plus B equals 5. And my green one was just fine. There were no x's in there already. And now my job is to figure out what's A and what's B. Remember, that's how we started this whole thing. We wanted to know what we could use for the partial fraction decomposition. So that means I need to solve this system. And thinking about some things that we've done recently, we could use inverses, we could use reduced row echelon form. I think I'll use an inverse for this one. So I'll have matrix A be the matrix with the coefficients 1, 1, 3, -5. And my X matrix would be A and B. And my B matrix would be 5, -1. And to solve AX equals B, X equals A inverse times B. So this one we could do by hand. This is a little 2 by 2, so we should. It's good practice. And the first thing we have to do is make sure that A is going to have an inverse by finding the determinant. So we multiply this times this, -5, main diagonal, and then we're going to go ahead and subtract this times this. So main diagonal 1 times -5 is -5. And then we have our secondary diagonal, which is 1 times 3. So -5 minus 3 gives us -8 for the determinant of matrix A. Now, that doesn't make me happy, but at least it's not a 0. That means I can find the inverse, because for the inverse, I'm going to need 1 over -8, which would be -1/8, times the elements of matrix A, where we switch the main diagonal and we negate the secondary diagonal. So my A inverse is going to have some fractions. It's okay, we can deal with fractions. So negative and a negative, 1/8 times 5 will be 5/8. -1/8 times 1 will be 1/8. -1/8 times -3 will be 3/8. And -1/8 times 1 will be -1/8. So at least we didn't end up with a whole lot of negatives in our inverse. It's always easier to work with positives. Now there's A inverse. We need to multiply that by B, which is 5 and -1. So let's see what we get. Row 1 times column 1 and add the results. So 5/8 times 5 would be 25/8. 25/8 plus -1/8 is 24/8, which is 3. And we realize we have a 2 by 2 and a 2 by 1, so our result should be a 2 by 1 when we get done. Then we go ahead and go to row 2, column 1. 3/8 times 5 is 15/8. -1/8 times -1 is 1/8. 15/8 plus 1/8 would be 16/8, which is 2. So our solution matrix that we have here is going to be 3 and 2. Now, let's go ahead and see what that looks like. Using this for A and B in the original. Remember, we said we were going to put A, let me scroll up so you can see it. A over x minus 5 and B over x plus 3. So right now we are saying we have found this. 3 over x minus 5 plus 2 over x plus 3 will give us exactly what we need. Now, that's the partial fraction decomposition. So way up at the top, it had said, find the partial fraction decomposition of these two. And we did. So now what we need to do is support our answer graphically, which means what we want to do is take a peek at this and see if something is happening with our graph that we would notice by looking at this partial fraction decomposition. And this takes us back a long ways, because what we would do is think vertical asymptotes. This one should have a vertical asymptote at x equals 5, and this one at x equals -3. And take a little look at, does that match what we have for the graph of this? So I'm going to stop this for just a second so that I can put that graph in and we can actually take a look at it. There is our function. We've got the 5x minus 1 over the quantity x squared minus 2x minus 15. We hit zoom 6. And we wonder, I wonder if that really has a vertical asymptote at 5 and -3. Well, let's see. 1, 2, 3, 4, 5. 1, 2, 3. Looking good, but to be sure, we could do second table and check out our numbers and make sure that our asymptotes were where we thought they were going to be. And of course, it's going a little slow. And we see that 5 has an error. And that -3 has an error. And that's exactly what we needed to see. We needed to see that our asymptotes were really where they should be, and that our partial decomposition is going to work. Now, to be extra certain, in y sub 2, we could punch in our statement, which would be our fraction 3 over the quantity x minus 5 plus 2 over the quantity x plus 3 would graph exactly the same as the original. And because this thing is so slow, I won't do this, but that would be a really good way to check. You have to make sure it gives you exactly the same thing. I'm gonna pause it and I'm gonna put it in. I want you to see that it will give us the same thing. All right, so I've punched in our answer, which was 3 over the quantity x minus 5 plus 2 over the quantity x plus 3. And when I hit graph, my hope is that it is exactly the same graph. So we should see the next color go right over the top of the blue. And there comes the red. It is exactly the same graph. So that means our partial fraction decomposition was correct, and that's what we want to see. So now we've got one of these done. Let's see what we can do here as we move further and further into those objectives of completing this partial fraction decomposition. So decomposing a fraction with a repeated linear factor. Find the partial fraction decomposition, and the first thing we would do is see whether or not, well, first of all, can we do the division, but the degree on the top of this is less than the degree on the bottom, so we're not going to be doing the quotient with the remainder. We're just going to go right into how can we factor that denominator. So we've got -x squared plus 2x plus 4. We should always check to see if the degree of the numerator is greater than the degree of the denominator, because that means we can actually do the division, and we should. Then on the bottom, I notice a lot of x's. So I pull an x out, and I have x squared minus 4x plus 4. Now that looks a lot like a perfect square trinomial. So let's take a peek. X squared is x. 2 squared is 4. 2 times x doubled is 4x. So this is -x squared plus 2x plus 4 over x times x minus 2 squared. So this is where we see that we have a repeated linear factor. So I think about my partial fraction decomposition and I realize I'm going to have an a over x. I'm going to have a b over an x minus 2, but I'm also going to have a c over x minus 2 squared because we have to have every single one of those factors as possibilities for our denominator. So we'd increase and keep going and see what we have. So now we realize, well, in order to put this together, we've got our job cut out for us because we are going to need a common denominator. And it's not as bad as it first looks, but this one is a little more involved. So my first fraction over here is going to need an x minus 2 squared on the top and the bottom. The middle one, going to need an x and another x minus 2. And the last one is just going to need an additional x. Now, the denominators no longer matter because I have them all the same. They're all going to be x times x minus 2 squared. So instead, I'm going to focus my energy on the numerators because that's where our answers are going to come from anyway. Now, I have to see what A, B, and C are going to do to all of these terms. There's going to be x squared terms and x terms and constants. So I'm going to have to go ahead and figure out what x minus 2 squared was. The good news is we already know because we just factored that up above. That was x squared minus 4x plus 4. You certainly could write out x minus 2 times x minus 2 and do the FOIL yourself. But this will be bx squared minus 2bx plus cx. And then one more time with distributing, we'll have ax squared minus 4ax plus 4a plus bx squared minus 2bx plus cx. So now is roundup time. We're doing a roundup. Here's what we have to do. We have to round up all the squared terms. So I see that I have an ax squared plus bx squared. Then we have to round up all the x terms. So I have a negative 4ax and a negative 2bx. And then we have to round up all of, oh, forgot one, my cx down there. There's all of those. And then we have to round up just our constants. So we've got the 4a. Now notice I'm trying to keep these lined up as A, B, and C in columns as I go through this. So now I realize, well, I know what these had to be because I had the answer way up here. I have to get a negative x squared, a 2x, and a 4. That has to happen. So I think about what I had for my x squareds, and I realize, well, my x squareds are going to have to add up to a negative x squared. And all of my x's, well, those are going to have to add up to 2x. And my constants, well, my constants have to add up to 4. So this is going to be my system minus the x squareds and the x's. I don't need those. I already have all of this lined up by row, so all I need are the numbers. So I'll have a plus b equaling a negative 1, a negative 4a minus 2b plus 1c equals 2, and 4a equals 4. And if you're thinking like I am right now, this one would not be something we would necessarily need to use matrices for, because we've got 4a equals 4 down there at the bottom, pretty obviously. So you maybe don't even want to use matrices with this one. But let's continue on. And with this one, we've got 1a, 1b, no c, and -1 as our constant, -4a, -2b, and 1c, and 2 is our constant, 4a, 0b, 0c, and a 4 as our constant. Now notice for this one I went ahead and did the augmented matrix. You certainly could still use the inverses if you wanted to, because we would have a square matrix for the coefficients, but it might be a better use of our time if we just did RREF, reduced row echelon form. So let me pull the calculator back up here and clear out what we were doing with the graph and get into the matrices. So second inverse, and I went ahead and put in matrix A. So I should show that to you just so that you can see it. Second matrix, there it is. So we have our 1, 1, 0, -1, -4, -2, 1, 2, 4, 0, 0, 4. And we want to do reduced row echelon form. So second quit, second matrices, math, and then I'm just going to hit alpha and B to get down to our REF. And then we do recalling the name of the matrix, second inverse, number 1, finish that off, and there it is. So here's what it's telling us. It's telling us that A, B, C, A is 1. A, B, C, B is -2. A, B, C, C is 2. So A is 1, B is -2, and C is 2. Now that's the same thing we would have gotten if we had done this one by hand, because like I said, it's really hard to resist the 4A equals 4, so A equals 1, and then put that back up in here and realize that you have 1 plus B equals -1, subtract 1 from both sides and get B equals 2. And then we've got the last one, which we could just do substitution for, but we're going to get the exact same answer. So A is 1, B is -2. Oh, and I wrote positive and 2 down. There we go. And then C comes out to 2. Now we want to finish it up. We want to go back and remember what it was we had A over the top of, what we had B over the top of, and what we had C over the top of. And I always put those in order so that I've got my A, B, and C. And then we're going to go ahead and put them where they're supposed to go. So our A value was 1. So 1 over X. Our B value was -2. We are going to write this. This is one of the rare times when we say plus a negative. You know how I feel about that because it's not simplified, but it definitely shows that partial fraction decomposition. And then our C value of 2 over X minus 2 squared. So there's our partial fraction decomposition, and lots of different ways to solve it. You know, by hand with the A's and B's and C's, using the matrices, it just inverses matrices or reduced row echelon, lots of different choices. And because this section actually in the book had other methods for using for decomposition of fractions, but we went and talked to the calculus teacher and found out, no, this is the way it should be done. This is how they want you to do it. So when it says an alternative method, we're just skipping that. We're not going to do an alternative method. We want to keep using the method that we already have. So let's see if I can get one more of these in with you. The good news with this one is we already have a factored denominator. So this one is use this method to find a partial fraction decomposition. So we'll have A over the quantity x plus 2 plus B over the quantity x minus 3 plus C over the quantity x minus 3 squared. And again, what we're going to do is pretend that these are the denominators that we have to work with. We've broken those apart, and that we have to build them up in order to do the addition and get this for an answer. So like I said, it was already factored. We can see that the x's in the denominator, if we multiplied all them together, would be x cubed. X squared is definitely higher than x cubed, so we wouldn't go through the process of the division. Now, this one's going to need an x minus 3 squared on the top and the bottom. This one is going to need an x plus 2 and one more x minus 3. And the last one is going to need an x plus 2. And we realize our denominators are going to be like denominators. We just built them up that way. So we'll need A times the quantity x minus 3 squared plus B times the quantity x plus 2 times the quantity x minus 3 plus C times the quantity x plus 2. My C's and my parentheses are looking way too much like each other here. That's a little bit better. All right, so now we need to know what x minus 3 squared is. Well, that's x minus 3 times x minus 3. So that'll be x squared minus 6x plus 9 plus B, use some FOIL on the quantity x plus 2 times the quantity x minus 3. X squared minus 3x plus 2x will be minus 1x minus 6. And then we have C times the quantity x plus 2. Now let's go ahead and distribute. Ax squared minus 6ax plus 9a plus bx squared minus bx minus 6b plus cx plus 2c. And now we can go ahead and set these up. We're going to do our roundup, and we'll notice we have ax squared minus plus bx squared. So there's our x squareds. And then we have the x's, which is minus 6ax minus bx plus cx. And then all of our constants, 9a minus 6b plus 2c. And we go back up to the top and see that we had 5x squared, so this will have to equal 5x squared. Then we had negative 21x, and we have 13. Well, we're closing in on it here, so let's take the x's out of the picture, and we'll have a plus b equals 5. Negative 6a minus b plus cx so we get the negative 21, so it's negative 6a minus b plus c without the x's in there equals negative 21. 9a minus 6b plus 2c equals 13. And we can make an augmented matrix. 1, 1, 0, 5, negative 6, negative 1, 1, negative 2, 9, negative 6, 2, and 13. And use the RREF, reduced row echelon form of that matrix, and find our solutions. So we have the matrix all designed for what we need here. It's just a matter of finding those solutions, and the easiest way to do it, the quickest way, is going to be our REF. So I went ahead and put our matrix in there, our 3 by 4, already set. and we need to do second, inverse, math, down to our REF, which is alpha B. So I'd just as soon punch that in rather than having to go through the whole thing. Oh, look at that. It didn't go back to the main screen on me. Just love this calculator on the smartboard here. All right, so second, matrix, math, alpha, B, and then second, inverse for matrices, number 1, parentheses, enter. So this is telling us that our A is 3 because again the columns are A, B, and C. So A is 3, B is 2, and C is -1. So this is the part that brings it all together. You know, when we can say, okay, now we have our values for A, B, and C. Go back up to remember what it was we used for our denominators. And you can see them right here. The x plus 2, the x minus 3, and the x minus 3 squared. And then I'll scroll back down and we'll write what we had. So our answer for A was 3 over the x plus 2, and our B value was 2 over the x minus 3, and then plus a -1. And as I mentioned before, this is one of the rare times when you can get away with that because it really shows how you did the partial fraction decomposition. So this, if we got a common denominator, would give us what we started off with at the beginning, which was 5x squared minus 21x plus 13 over x plus 2, the quantity x plus 2, times the quantity x minus 3 squared. And you could check it again. Remember, we did this in the calculator before. You could make this y sub 1. Very carefully punch all of this in as y sub 2, and you should see the exact same graph. All right, that is everything that I really felt we had to get through for this first day. And we'll get some more practice on this again after the MCA testing. So we'll have a little break in here. Don't forget all the fabulous things that you are supposed to bring for the MCA testing. But for this section, section 7.4 day 1, we're looking at page 562, numbers 1 through 6, 8 through 10, and 13 to 25, the odd, to give you some good practice at our objective of decomposing our fractions. And you might need to pause this. I'm going to go ahead and stop the video so that it's not adding more time on here.